Good morning, students. Welcome to Bindu Dhadwal chemistry lessons. We will continue the effect of substituents on the acidic strength of benzoic acid today, and we will also do some chemical reactivities of carboxylic acids. So let's begin. The acid weakening effect of the electron donating group and acid strengthening effect of electron withdrawing group is more pronounced at para position than at meta position. So as we know that electron withdrawing substituent nitro increases the acidic character. So when nitro is at para position, it will increase the acidic character more than when it is at meta position. So accordingly, ortho-nitrobenzoic acid will be the strongest acid. This is because of ortho effect. Then para-nitrobenzoic acid will be stronger than meta-nitrobenzoic acid, and this will be stronger acid than benzoic acid, which does not contain any electron withdrawing group. On the other hand, electron releasing group will weaken the acidic character. So electron releasing groups like OH group, meta isomer will be stronger acid because weakening effect is also more pronounced at para position. So this will be the weakest acid, and meta will be stronger than the para hydroxybenzoic acid. So when the electron releasing group is hydroxy group, in that case again ortho hydroxybenzoic acid will be the strongest acid, then meta, then benzoic acid, and then para hydroxybenzoic acid. So we see that ortho isomer of every substituted benzoic acid is the strongest acid among the three isomers, ortho, meta, and para. No matter whether the substituent is electron withdrawing or electron releasing. This effect is called ortho effect. It is a combination of both steric and electronic factors. Study the effect of substituents on the acid strength on the basis of combined effect of inductive effect, resonance effect, and ortho effect. So if we take all these three factors in combination, we see that when the substituent is an electron donating group, then methyl, if the electron donating group is methyl, then ortho is more acidic than benzoic acid, than meta methyl benzoic acid, than para methyl benzoic acid or para-toluic acid. When the electron releasing group is OH, then ortho is more acidic than meta, than benzoic acid, than para-hydroxybenzoic acid. If the electron releasing group is amino, then benzoic acid is the most acidic, meta-aminobenzoic acid is less acidic than benzoic acid, ortho is less acidic than meta-aminobenzoic acid, and para-aminobenzoic acid is the weakest acid. When the electron releasing group is methoxy group, ortho-methoxybenzoic acid is stronger acid than meta-methoxybenzoic acid, than benzoic acid, than para-methoxybenzoic acid. We'll show this acidic trend. Ortho-nitrobenzoic acid will be more acidic than para-nitrobenzoic acid, which will be more acidic than meta-nitrobenzoic acid, and nitrobenzoic acid. And benzoic acid will be the weakest acid. And chloro is also an electron withdrawing group. So orthochlorobenzoic acid will be strongest acid, than metachloro, than parachloro, than benzoic acid. Comparison of relative acidic strength of monocarboxylic acids, alcohols, and phenols. So carboxylic acids are stronger acids than alcohols. Carboxylic acid will give proton to water to form hydronium ion, and itself it will form carboxylate ion, which is resonance stabilized. So the carboxylate ion is more resonance stabilized than the alkoxide ion, which does not have resonance stability. So carboxylic acid is stronger acid. Carboxylic acids and phenols. Phenols are acidic because phenoxide ion can be stabilized by delocalization of negative charge into the ring. However, phenols are less acidic than carboxylic acids. If we compare the resonance hybrid of carboxylate ion and phenoxide ion, in case of carboxylate ion, the negative charge is dispersed on 2 electronegative oxygen atoms, whereas in phenoxide ion, the negative charge is dispersed on only 1 oxygen atom. Electron charge in carboxylate ion is more dispersed when compared to phenate ion, since there are 2 electronegative oxygen atoms in carboxylate ion as compared to only 1 oxygen in phenate ion. Moreover, carboxylate ion is stabilized by 2 equivalent resonating structures in which the negative charge is on the more oxygen atom. And in case of phenoxide ion, it has non-equivalent resonance structures in which the negative charge is on the less electronegative carbon atom of the ring than on the more electronegative oxygen atom. So carboxylate ion is more stable than phenoxide ion, and carboxylic acid is better acid than phenol. The acidic strength of compounds in general follows the order. Carboxylic acids are most acidic. Alkynes are less acidic than alcohols. Alcohols are less acidic than water. Water is less acidic than phenol, and phenol is less acidic than carboxylic acids. For common groups attached to CH3COH, the acidic strength increases as propanoic acid will be weakest acid, having highest pK value, then acetic acid, then phenyl acetic acid, then hydroxyacetic acid, then chloroacetic acid. Chloroacetic acid is the strongest acid. To sum up, common acids are arranged in following order of acidity. Trifluoroacetic acid is the strongest acid, then is trichloroacetic acid, then dichloroacetic acid, then nitroacetic acid, then cyanoacetic acid, then monofluoroacetic acid, then chloroacetic acid, then bromoacetic acid, then formic acid, then chloropropanoic acid, then benzoic acid, then phenyl acetic acid, then acetic acid, and then propanoic acid. So propanoic acid is the weakest acid. Acidic character of carboxylic acids can be shown by the following reactions. They react with blue litmus and turn it red. They are acidic in nature. They react with metals to liberate hydrogen gas, acetic acid plus sodium, sodium acetate plus hydrogen. Similarly, benzoic acid plus sodium, sodium benzoate plus hydrogen. They react with alkalis to form salt and water. Acetic acid plus sodium hydroxide will form sodium acetate plus water. They react with carbonates and bicarbonates, liberating carbon dioxide in the process with brisk effervescence, because brisk effervescence are produced with carboxylic acids and not with phenols. This reaction is used to distinguish between carboxylic acids and phenols. Reactions involving the OH group of the carboxylic acid. This is category B. So in RCOH, bond breaks from this end. OH is replaced with groups like Cl, OR, NH2 and RCO negative. So the compounds that will be formed will be chlorides or esters or amides or anhydrides. These are functional derivatives of carboxylic acid. When carboxylic acid is used to form these compounds, these are derivatives of carboxylic acids. So let us form these compounds one by one. First is formation of RCOCl. OH is replaced by Cl. This is acid chloride. So acid chloride can be formed from carboxylic acid by reaction with phosphorus pentachloride, trichloride, or thionyl chloride. So carboxylic acid plus phosphorus pentachloride will form RCOCl plus POCl3 plus HCl. PCl5 reacts in this manner. PCl3 with oxygen, 1Cl with H, and 1Cl with RCO. So RCOCl, POCl3 and HCl are formed. With the phosphorus trichloride, 3 carboxylic acid will combine. 3 OH will be replaced by Cl to form acid chlorides. 3 RCOCl and H3PO3 will be formed. Similarly, with thionyl chloride, SO will attach with oxygen to form SO2. 1 Cl will react to form acid chloride, other Cl will react to form HCl. So RCOCl, SO2 and HCl are formed. Similarly, benzoic acid also reacts in the similar manner. Then when acids are made to react with alcohols in presence of concentrated sulfuric acid, the OH of acid combines with H of alcohol to form water, and these two combine to form the ester. So sweet smelling esters are formed. This reaction is called esterification reaction. Now this is a reversible process, so the reaction can be made to go in the right side, in the forward direction, if either we remove water after its formation, or we use excess of reactant alcohol. So ester will be formed. Then because of steric hindrance factor, the reactivity is such that tertiary alcohols will be least reactive than secondary alcohol, than primary alcohol, and methanol will be most reactive. Similarly, in carboxylic acids also, the least substituted formic acid will be most reactive. Tertiary acids will be less reactive than secondary, with less reactive than primary alkyl carboxylic acids. Esterification of carboxylic acids with alcohols is a nucleophilic acyl substitution reaction. So the mechanism involves, first the acid will take up a proton to form dihydroxy compound where oxygen has a positive charge. To ease off the positive charge, the electrons of the double bond move towards the oxygen, resulting in a positive charge on carbon. So because of this, as a result of protonation, this carbonyl carbon gets activated and undergoes the attack by lone pair of electrons on the oxygen atom of the alcohol. So it is having a lone pair of electrons and acting as nucleophile. This nucleophile will attack this carbon atom to again form a tetrahedral complex where we have R, C, OH, OH and ROH on this side. Okay, oxygen again has a positive charge. In this next step, the resulting intermediate, there will be a proton shift to the OH group to form another tetrahedral intermediate with positive charge on oxygen. So the proton of alcohol moves here to form OH2 and a positive charge resides on this oxygen atom. In the next step, the water will move away and these electrons will come back to form R double bond OH and OR. Now this H will be removed. Last step is protonated ester will lose this proton to form RCOO R-, which is the ester. Formation of amides. So first an ammonium salt is formed and then it decomposes on heating to form amide. Similarly, acetic acid plus ammonia will form ammonium acetate, which decomposes on heating to form acetamide and water. Benzoic acid plus ammonia will form ammonium benzoate, which on heating will form benzamide and water. Formation of acid anhydrides. So phosphorus pentaoxide is a dehydrating agent. When two acids are made to react with each other in presence of dehydrating agent phosphorus pentaoxide, water is removed and these two join to form acid anhydride. Acetic acids will combine to form acetic anhydride. Benzoic acid will combine to form benzoic anhydride. Acid anhydride can also be formed by reaction between acetic acid and acetyl chloride in presence of pyridine. So HCl is formed and acid anhydride is formed. We can also react acid chloride with sodium salt of acetic acid in the presence of pyridine to form acid anhydride. Third category is reactions involving the carboxyl group as a whole. So first is decarboxylation. When sodium salt of carboxylic acid is heated with soda lime, a mixture of NaOH and CaO in the ratio of 3:1, the NaO and NaCO part combines to form Na2CO3 and H combines with R to form RH, which is the alkane. So the alkane that is formed has one carbon less atom less than the parent compound. This reaction for the formation of methane is the laboratory method of preparation of methane. Sodium acetate will react with soda lime to form methane and sodium carbonate. The methane that is formed has one carbon less than the sodium acetate that was used, which had 2 carbon atoms. A carboxylic acid containing an electron withdrawing group on the beta position, such as C double bond O or NO2 group, will readily undergo decarboxylation on heating to form, only CO2 is taken out to form CH3CO, CH3. So acetone. When 2 carboxylic acids are attached to the same carbon atom, again on heating they will lose 1 carbon dioxide to form CH3COH. Malonic acid will form acetic acid. Electrolytic decarboxylation. So when aqueous solution of sodium or potassium salt of carboxylic acid is electrolyzed, they decompose, they give off carbon dioxide, they undergo decarboxylation to give alkanes with even number of carbon atoms. So the reaction occurs, for example, potassium acetate, when electric current is passed through it, it decomposes into acetate ions and potassium ions. At anode, acetate ions lose electron to form acetates, which are unstable. So they give off carbon dioxide, forming methyl free radicals. 2 methyl free radicals combine to form ethane. So ethane is formed. At cathode, potassium ion will gain electron to form potassium atom, which reacts with water to form potassium hydroxide and hydrogen. So hydrogen gas is liberated. Then calcium salts of fatty acids also decompose and lose off their carbon dioxide in the form of calcium carbonate. So when calcium formate is distilled, formaldehyde is formed and calcium carbonate. CaCO3 is given off and HCHO combines. When calcium formate is distilled with acetaldehyde, 2 molecules of calcium carbonate will be formed and CH3CHO will be formed. When calcium acetate is distilled, then calcium carbonate will be formed and CH3CO, CH3 will be formed, acetone will be formed. And when calcium formate is distilled with calcium benzoate, again calcium carbonate, 2 molecules are removed and C6H5CHO is formed, benzaldehyde is formed. Next reaction is reduction reaction. So on reduction with lithium aluminium hydride or with hydrogen in presence of copper chromide, the carboxylic acids get reduced to alcohols. But if we use hydrogen iodide with red phosphorus, then carboxylic acids get reduced to alkane with the same number of carbon atoms. Action of bromine on silver salt of the acid. When silver salt of carboxylic acid is heated with bromine in presence of carbon tetrachloride, carbon dioxide is lost and an alkyl halide alkyl bromide with less number of carbon atoms is formed along with carbon dioxide and AgBr. So this reaction is called Hans-Stecker reaction. Reactions involving alkyl group of carboxylic acid. So RCO, this alkyl group is active. So carboxylic acids having an alpha hydrogen atom will react with chlorine or bromine in presence of red phosphorus and then water, where alpha hydrogen will be replaced by halogen. So alpha chloro carboxylic acid is formed. Similarly, when acetic acid reacts with chlorine in presence of red phosphorus, HCl is lost and CH2 chloroacetic acid, CH2COHCl is formed. Chloroacetic acid can undergo further chlorination to form dichloroacetic acid. It can undergo another replacement substitution to form trichloroacetic acid. As long as there are alpha hydrogen atoms, halogen can substitute them. This reaction is called Helvolhart Zielinski reaction. The function of red phosphorus is to first combine with bromine to form phosphorus bromide, which then reacts with the carboxylic acid to form bromide. This acid bromide will get converted to its enol form, which will react with the ketone form to form this 2-bromoproponyl chloride, which will then react with acetic acid and form alpha haloacetic acid. The halogen atom in monosubstituted acid can be easily replaced by suitable atomer group to form a variety of compounds. For example, when we react it with aqueous KOH, OH takes the place of Cl to form hydroxyacetic acid. KCl will be formed. If we react with alcoholic ammonia, HCl will be formed, NH2 gets attached, so glycine will be formed. If we react it with KCN, Cl is replaced by cyano group to form cyanoacetic acid, which can on further hydrolysis form malonic acid, dicarboxylic acid. Then ring substitution can also occur. Carboxylic group is electron withdrawing in nature, so it will be a meta-directing group and the atom will be directed to the meta position of the carboxylic acid. So when benzoic acid is reacted with bromine in presence of Lewis acid, ferric bromide and heated, the 3-bromobenzoic acid is formed. Similarly, on reaction with sulfuric acid, 3-sulfobenzoic acid is formed, and on reacting with nitrating mixture of nitric acid and concentrated sulfuric acid, 3-nitrobenzoic acid is formed. This carboxylic acid does not undergo Friedel-Crafts reactions. This is because the carboxyl group is strongly deactivating in nature. Catalyst AlCl3 gets bonded to carboxyl group strongly instead of forming alkyl or acetyl derivatives. If OH or NH2 group is present ortho to carboxylic acid group, then in that case, when it's made to react with bromine water or nitrating mixture, carbon dioxide is removed along with substitution reactions. So 3 bromo groups will be attached at 2,4,6 positions to form 2,4,6-tribromophenol or 2,4,6-trinitrophenol, which is also called picric acid. So decarboxylation occurs, along with it substitution also occurs. That's all in today's video. If you like the video, please do share and subscribe.